Hello everyone, welcome to Math 115, College Algebra. So in this section, 11.1 from your textbook, we're going to talk about solving systems of linear equations in two variables. And we'll solve them using several different methods. So we'll solve it by graphing. I'll show you that first, which is not the most accurate method, but it gives you a visual of what's going on. We'll solve them by something called substitution, and then using the addition or elimination method as well. And then at the end, we will solve some applications involving systems of linear equations in two variables. Okay, so the first thing I want to mention is that there's basically three types of linear systems. So one type is like this, and this is going to be the most common one, where we have two linear equations, right, which are represented by two lines. So say something like this, and they go on forever. And the solution is where those lines intersect. So that point right there, right, that ordered pair, that would be the solution. So this is the most common case where there's one solution. Okay, you could have a case where the lines are actually, they may not look it at first, but they're actually the same line. So they lie right on top of one another. It's hard to even draw this. I'll do it like dashed. So assume that dashed one lies right on top of it. So in this case, all of these points are solutions, right? Because they're basically the same line, same equation. So in this case, you would say that there's an infinite number of solutions. So infinite number of solutions. And it's because they're really the same line. Like one equation is a multiple of the other. Okay, so I'll say same line. And then I'll note that one equation is a multiple of the other. Okay, and then the last possibility is that the two lines that represent the two equations are actually parallel. And in that case, if they're parallel lines, then there's no solution, right? There's nowhere where they intersect. So this would mean that there's no solution. Right? Remember, a solution is an ordered pair that makes both equations true. So graphically, that would be where the two lines intersect, or in this case, where you have an infinite number of solutions, they intersect at every point, right? So all ordered pairs would make both equations true in that case. But the most common case is this first case right here, where we're just going to have one solution. Okay, so this last one, where we have parallel lines, this is called an inconsistent system. And then the first two are consistent. So these first two are consistent systems, which basically means there's at least one solution. Again, the most common case is going to be this first case. Okay, so actually let's start off with an easy example. Let's say I want to just verify that a particular ordered pair is a solution to a system. So in this example one, I want to verify that the ordered pair, the point 4, 7, is a solution to that system of two linear equations. So here's my system, right, of the two linear equations, and I want to see whether 4, 7 is a solution to that system. So to check this, remember the first value is going to be our x, the second is going to be our y. Plug that ordered pair into both equations, and it must be true for both equations. Then it will be a solution. If it's only true for one of them or for none of them, then it's not going to be a solution. Okay, so literally we just plug in. So I'll plug in ordered pair, and it must be true for both. Both equations. Okay, so if I plug in to the first equation, 4 for x and 7 for y, I want to see whether that equals 15, right? So 2 times 4 is 8 plus 7. Yeah, 15 equals 15. So it checks the first one. It's definitely a solution to that first equation. What about the second one? So I have 3 times 4 minus 7. Does that question mark equal 5? Well, this is 12 minus 7. Yeah, that's 5 is equal to 5. So in this case, yes, it is a solution to the system. So yes, 4, 7 is a solution to the system. And what does that mean graphically? It's where the two lines cross, right? Assuming these are not multiples of one another, then it would be that case where there's an infinite number of solutions. But in general, if you just have random two linear equations, they're going to cross at one point. Okay, so how do we solve these systems to come up with the answer? Here we just check the answer, but how do we solve them to come up with the answer? Well, one way of doing this is we can do this graphically. Okay, so I could graph both of the equations, and then where they cross, that must be the solution. All right, so how would I do this graphically? Let's see if we can solve this example right here. So first of all, let's write it in the form y equals mx plus b, because I think it's just easier to see everything that way. So I'll write down the first equation, 2x plus y equals negative 8. And then I'll solve it for y. I'll subtract 2x on both sides. So I have y equals minus 2x minus 8. Okay, ultimately I want to graph this, so let me draw a graph over here. I don't really know how many tick marks, but I'm going to put like at least 8 of them. Okay, so that's x, this is y. All right, so how would I graph this? Well, you could graph this a couple of ways, right? You could find the y-intercept, which we know the b is negative 8, so it'll be 0, negative 8, and then use the slope to figure out the next point. Or I could just make a little table and pick a couple of points. So actually, let me do the y-intercept. So when x is 0, y is negative 8. And then I guess I could do the x-intercept as well. So now if y is 0, like what is x? It must be negative 4, right? If I set y equal to 0 and I solve this for x, so I need to add 8. I'm going to have negative 2x equals 8, divide by negative 2. So x is equal to negative 4. Do the same thing with the second equation. So here I have x minus y is equal to negative 1. So I'm going to solve this for y. So I have negative y equals negative x minus 1. Then when I divide by negative 1, this is going to be y is equal to x plus 1. Right? It'll be negative x over negative 1, which is positive x, plus negative 1 over negative 1, which is positive 1. And then, again, I'll just use the x and y intercepts. So for the y-intercept, if x is 0, y is 1. And then if y is 0, we can just see this, right? If I plug in 0 for y, x must be negative 1. All right, so if I plot these points, So let me do the first line. 0, -8 is here. And then -4, 0 is here. So this first line is going to look something like this. All right, and it goes on forever. And then for the second line, I have 0, 1, which is here, and then -1, 0, which is here. So the second line will look something like this. Okay, and the question is, where do they intersect? Well, if I drew this really, really well, and this is a problem with graphing, right, because it's not super accurate, they're going to intersect at the point, we can kind of see it here, -3, -2. Right, so that means the solution is x equals -3, y equals -2. So that would be the solution to that system of equations, right? Exactly where they intersect. Again, it's nice to see it graphically because it's very visual, but it's not very accurate. So it's visual, but not accurate. Because if our answer was, like 7/2 or something, or even something like, say, 3/16, let's say one of the values was, it'd be really hard to pick that out in a graph. All right, so it's nice to know how to do it graphically, but not very accurate. So let's review now some more accurate ways of actually solving these systems. Okay, so one method is called substitution. Okay, this method actually works best if you can easily solve one equation for one of the variables. However, you can use it regardless. You can use it for any system of two linear equations. So let me just read through the steps here, and then this will make more sense when we actually do examples. So the first step is to choose one of the equations and solve for one of the variables. If possible, and this is when it makes it easier, try to choose the easiest variable to solve for, such as a variable that has a coefficient equal to 1. Then using the other equation, you substitute in the expression for the variable that you just solved for in step 1. So now you're going to have the equation just in terms of the remaining variable. You can solve for that variable, and then once you have the answer to one of the variables, you can go back and plug it into one of the original equations. Usually you want to plug it back into the original equation that you manipulated, because it's already solved for the remaining variable. It's isolated, and you can solve for that remaining variable. Okay, so again, there's a lot there. Let's do an example to explain how this works. So I have my system, and if you look at that, it looks like it's pretty easy to solve for the y in the first equation. Right, so I'm going to say, so this is the first step, solve one of the equations for one of the variables. So I'm going to solve the first equation for y, right, because it's pretty easy to find that. In fact, all you have to do is add x to both sides. Equals -5. So if I add x, I'm going to get y is equal to x minus 5. Okay, now, second part. I go to the second equation, and where I have a y, I'm going to substitute in this expression, the x minus 5, right? So I go to the second equation, 2x minus 5, y, be careful, put parentheses, and the entire y now is x minus 5. That's got to equal 1. Notice now that this equation is just in terms of x, right? I can solve it now for x. So how would I do that? I would distribute in the -5. So I have 2x minus 5x. -5 times -5 is positive 25 is equal to 1. I can combine like terms, right? So this is -3x plus 25 is equal to 1. Then I need to subtract 25. So negative 3x is equal to negative 24. And then finally divide by negative 3. And I'm going to get x is equal to, what's that, positive 8, I guess, in this case. Okay, so I'm half done, right? That's one of my solutions, x equals 8. Now, how do I go back and solve for y? Well, I can either plug it into one of these original equations, or even easier is the one I manipulated, right? Because remember, this one, I already solved it for y. I've already isolated the y. So this is the easiest one. This is just the first equation that I rearranged. So I'm going to go back to that first equation and solve for y. So where I have an x, I'm going to plug in 8. And then 8 minus 5 is 3. So I'm going to get y is equal to 3. So that's my solution. X equals 8, y equals 3. And then, of course, as an ordered pair, it'd be 8, comma 3. That's where the two lines would cross if you were to graph them. Okay, let's do another example. Solve by substitution. All right, so remember the first step is to isolate one of the variables in one of the equations. Oh, this is nice, right? This first step is already done for us, right? So if you look at that first equation, we have x equals y plus 3, right? The first step, x is already isolated. So the first step is done. So now I go directly to the second step. In the second equation where I have an x, I'm going to plug in y plus 3. And now my equation is just in terms of y. I can solve it for y. So I'm going to distribute in the 3. So 4 is equal to 3y plus 9 minus 2y. Then combine like terms. So I have 4 is equal to 3y minus 2y is just 1y, right, which is y plus 9. And then finally, if I subtract 9, I'm going to get y is equal to negative 5. Okay, and then how do I find x? I go back in and plug it to one of the original equations. But again, you usually want to use the one that you manipulated. We didn't even have to manipulate it. It was already, right, solved for x. So I'm just going to plug it back into that first equation. X equals y plus 3. So where I have a y now, I'm going to put in a negative 5. And then what's negative 5 plus 3? That's negative 2. So x equals negative 2. So then the ordered pair, right, where the lines actually cross would be negative 2, comma, negative 5. That's where they would actually cross. Okay, so that's all there is to it for the method of substitution. The next method I want to talk about is elimination, or some people call this the addition method. Okay, so let me go over the steps for solving a system of two linear equations and two variables using the elimination or addition method, and then we'll do a bunch of examples. Again, it'll make more sense when we start doing the examples. So the first step is you want to write the two equations so that the x variable and the y variable, those terms are lined up on the left-hand side of each equation. And you want to put the constants on the right-hand side. Okay, then you're going to choose one of the variables to eliminate, right? Either x or y, or they could be named other things, but typically x and y. To do this, right, to eliminate the variable, we need to rewrite one or both of the equations, which means you need to multiply one or both of the equations by some value, by some constant, such that the coefficients of the variable that we want to eliminate are equal but opposite. So when we add them, they're gone. You basically get 0. Okay, that's what we mean by elimination. Once we've done that, we can add the equations together. You're just going to have one remaining variable. You can solve for that variable. And then finally, you plug the solution from that step 3, back into one of the original equations to solve for the remaining variable. Okay? Again, it sounds like a lot. This will make more sense when I do an example. So let's look at an example here. Okay, so first thing, make sure that the equations are lined up. Where the x's are lined up, the y's are lined up, and the constants are lined up on the right-hand side. In this case, this is fine, right? So the first step is already done for us, but you have to be careful. Let's say I gave you the original system like this. I'm just going to write it differently over here. It's the same thing. Just going to write it differently. And then let's say this was okay, it's exactly the same system, right? But first, you would need to rewrite this so that the x's and y's are both on the left-hand side. So you'd have to add 5y to both sides, and you're going to get this. And then in this case, you'd have to add the x to both sides, and you're going to get this. And then you line up the x's, the y's, and then leave the two constants on the right-hand side. Okay, so sometimes you're given a system like this, and you have to first rearrange it. So the variables are lined up on the left-hand side, and the constants on the right-hand side. Okay, but in many cases, that first step is done for you. But sometimes it's not, so you got to be careful with that. All right, so in this case, it's done for us. I want to say, if you look at this, let me write the system here again. The question is, what variable do I want to eliminate? Okay, if I wanted to eliminate the y's, right? Since I have a 5 and a negative 2 here, I'd want to make one of these coefficients to be, you basically want the lowest common multiple of this, and one of them positive, one of them negative. So basically the lowest common multiple of 5 and 2 is 10. So I'd want to make one of them positive 10 and one of them negative 10. I could do that by multiplying this equation by 2, right? The entire thing by 2 to make this a positive 10. And then if I multiply the second equation by 5, that'll make this a negative 10. And when I add them, the y's are gone. However, if you look at the x's, I have a 3 and a 1 here. If I make this a negative 3, then I don't need to do anything to the first one, right? I already have a positive 3. Then when I add them, I can eliminate the x's. So it's probably going to be easiest, right, to eliminate the x's in this case. I want this coefficient here. I want this to be a negative 3. Right, so that when I add them, I can get rid of the x's. So how do I do that? I have to multiply both sides of the second equation by negative 3. So negative 3, and I'm going to multiply both sides of that second equation. I'll write it down here. Multiply both sides of second equation by negative 3. All right, so I need to distribute into negative 3. I'm going to have negative 3 x plus 6y is equal to negative 33. Okay, now I can add the two equations together, right? So let me write the first equation again. And then the new second equation, right, that I changed by multiplying. I didn't really change the equation. I multiplied everything by negative 3. You can do that to both sides. But it's written in different form now so that I can eliminate the x's. I rewrote the second equation is a better way of saying it. Okay, again, why did I do that? Because now, look, if I add these, 3x plus negative 3x, that's gone. 5y plus 6y is 11y. And then negative 11 plus negative 33 is negative 44. Now I can solve this for y, right? It's just one equation in terms of y. So to get y, I'm running out of room here. I think I can squeeze it in. I'm going to divide both sides by 11. and I'm going to have y is equal to negative 44 divided by 11 is 4, right? So y is negative 4. So I'm half done. I have one of my variables solved for. So now I want to go and I want to plug that value, y equals negative 4, into one of the original equations. It doesn't matter which one. Actually, it looks like the second one's going to be easier, right? Because I want to solve it now for x. So, but it doesn't matter. Either one will give you the correct solution. So I'm going to plug back into one of the original equations and solve for x. I'm just going to choose the second equation. So where I have a y now, I'm going to plug in a negative 4. And then if I solve for x, this is plus negative 2 times negative 4 is positive 8, right? And then if I subtract 8, I'm going to get x is equal to 3. And that's my solution. So the ordered pair is going to be 3 comma negative 4. That would be my solution. Okay. Another example. So I'm going to solve this using elimination. Now, in this case, it doesn't look like one is easier than the other to solve because I have like different coefficients on both of these, on the x's and y's. First of all, step one is done, right? The x's are lined up, the y's are lined up, the constants are lined up. Make sure you do that if they're not already lined up. I don't know. Let's say we want to eliminate the x's again. So right now I have a 2 here and a 5. The lowest common multiple of 2 and 5 is 10. So I want to make one of these a positive 10 and one of these a negative 10. It doesn't matter which. So here, I'm going to write this again. So for this coefficient, let's say I want it to be a positive 10. And this one, I want a negative 10. Again, it doesn't matter. I could make the first one negative 10, the second one positive. I just want them equal and opposite, okay? So if I want to make that first equation a positive 10, that means I need to multiply by positive 5, right? So both sides, don't forget, you need to multiply both sides because you're not changing the equation, you're just rewriting it. And in the second equation, if I want a negative 10 there and I already have a positive 5, I need to multiply the second equation by negative 2. Again, both sides. Okay, so if I distribute the 5, distribute the negative 2, I'm going to have this. Let me do the first one first. So I have 10x, that was my goal, right, to get a 10 there, plus 15y is equal to 5 times 16, what, is 80, so negative 80. And in the second one, I have negative 2 times 5x is negative 10x. Great, that's what I wanted. Negative 2 times negative 10y is positive 20y is equal to negative 2 times 30 was negative 60. Now I can add them, right? When I add these, the x's are gone, right? 10x plus negative 10x is 0. 15y plus 20y is 35y. And then negative 80 plus negative 60 is negative, I guess, 140. And now to solve for y, I just need to divide by 35. Does 35? Yeah, 35 goes into this, right? Because 35 times 2 is 70. 70 goes in, so I guess it goes in 4 times. So it would be like y equals negative 4. That's nice. Okay, so now how do I go back and solve for x? Well, I can plug into one of these equations, right? Either equations, it doesn't matter. Maybe the first one's slightly easier because it's slightly smaller numbers, but they're about the same. So I'm just going to plug into the first one. So where I have a y, I can put in negative 4. So I have 2x minus 12 is equal to negative 16. Add 12, add 12. I'm going to get 2x is equal to negative 4. And then I'm going to divide by positive 2. x is equal to negative 4 divided by positive 2 is negative 2. Okay, and then that's my solution. So the ordered pair negative 2 comma negative 4, right? That would be the point where the two lines would cross. Okay, let me do one of the special cases just so you see how this works. Let's say I try to solve this system using the elimination method. Okay, so first of all, they're already lined up, so that's done for us. And let's say I want to eliminate the y's this time. We'll notice here the lowest common multiple of 2 and 4 is 4, right? So I already have a positive 4 here. I'd like to get a negative 4 here. Well, I can do that if I multiply this whole equation, both sides, by negative 2, right? So I'm going to multiply the first equation by negative 2. And again, don't forget to do both sides. So this is going to be negative 8x negative 4y is equal to positive 36. Okay, so now if I add that, so the first equation again but is just rewritten, and I add that to the second equation. All right, so I can eliminate the y's. But look what happens in this case. Not only are the y's eliminated, but the x's, so the y's are eliminated, the x's are also eliminated. I get 0 is equal to, and on the right-hand side, the constants are eliminated, right? 36 plus negative 36 is 0. So this 0 equals 0 is always true. So what does that mean in terms of solutions? It means that there's actually an infinite number of solutions. Okay, so what does that mean in terms of the system? This was actually a dependent system. And you can kind of see here why. This second equation is just a multiple of the first equation. So in reality, these two equations are not different, right? That second equation is twice the first equation. Right, so I'll say this: the second equation was a multiple of the first equation. And in fact, it was twice the first equation, right? Because if I multiply the first equation by 2, so if I do both sides by 2, I'm going to get 8x plus 4y is equal to negative 36. And that's exactly the second equation. Okay, so whenever one equation is a multiple of the other equation, then you're going to have this dependent system. And when you try solving it, so you can go ahead and try solving it, you're going to end up with this 0 equals 0, which is always true. Then you know that one equation was a multiple of the other, and you have an infinite number of solutions. Now, how do we know if we have no solution, like the two lines are parallel? That would just be a case where one of these values, if the right-hand side does not add to 0, right? So if the left-hand side adds to 0, let's say the x's and y's are eliminated, but the right-hand side was like 3 or negative 7 or something, was not 0, then that's never true, and that would be a case where the two lines are parallel and there's no solution. Okay, so those are like the two special cases. All right. So next, I want to talk about some applications, right, or word problems that involve systems of linear equations. We'll do a few problems where we can use this idea to solve some applications. Okay, so let's look at some examples. So the first example, this is a very common type of problem for a system of linear equations and two variables. It says the admission fee at an amusement park is $2.75 for children and $5.20 for adults. On a certain day, 270 people entered the park, and the admission fees collected totaled $1,061. How many children and how many adults were admitted? All right, so to start, first of all, you want to read the question carefully, right, to make sure you understand what's being asked of you. And ultimately, we're trying to find the number of children and number of adults that attended this amusement park. So we want to create variable names, right? You could use X and Y, but that's not going to be as... You want to use some more meaningful names. So I would say, like, maybe let's A equal the number of adults, and maybe C equal number of children. Okay, so again, first step is always create variable names for the unknowns, right? The things that we're looking for. We're looking for a number of adults, number of children. Okay, now we need to come up, remember this whole idea is just solving two systems, or a system of two linear equations with two unknowns. So we need to come up with those two equations. Well, if we look at this information here, the first piece of information is sort of based on the number of people attending. We're told that 270 people total attended. So our first equation must involve the number of people attending, right? And we can think of it as the number of adults, A, plus the number of children, that must equal 270. Right? So that equation is basically just dependent on number of people attending the amusement park. Okay, and then we're also given information about how much it costs for a ticket for each child and each adult and the total amount of money that's collected. So the second equation must depend on basically the total amount of money that's collected. So how do we figure out how much money is collected from all the adults? Well, if each adult is paying $5.20, then it must be that 5.20 times A, right? So $5.20 times the number of adults. That'll be the total amount of money collected by the adults plus 275 times C. That'd be the total amount of money collected from all the children. That's got to equal the total amount of money collected, which is 1,061. Okay, so those are our two equations. All right, now sometimes people will want to eliminate the decimals, and you can do that by multiplying that second equation by 100. That's an option, right? Again, you're not changing the equation, you're just rewriting it, so you have just whole numbers. But you don't need to do that. You can if you want. Let me emphasize that the second equation was the total amount of money collected. Right, so the two equations, first one was the total number of people attending, second one involved the total amount of money collected. All right, so now that we have our two equations by two unknowns, we can solve it, we can use substitution, we can use elimination. Again, if you wanted to, you could make that second equation nicer by multiplying both sides by 100, just so you have all whole numbers. Let's just leave it in terms of decimals, and let's use substitution in this case. So I'm going to solve for A in the first equation. Remember, substitution, we have to solve for one of the variables and one of the equation. So you can use substitution or elimination, right? It doesn't matter. I'm just going to choose to use substitution. And since that first equation is not too difficult, I'm going to solve for A. So basically, I'm going to subtract C from both sides, right? So I have A equals 270 minus C, or I can write it as negative C plus 270. Okay, once I have that, what do I do with it? Well, I go to the second equation, and where I have an a, I'm going to plug in that expression, negative c plus 270. So I have 5.20, where now I have an a, I'm going to plug in negative c plus 270 plus 2.75c is equal to 1061. And it's an equation just in terms of c. I can solve, right? So I'm going to distribute in the 520. So I have minus 5.20c plus, if you multiply 5.20 times 270, you're going to get, let's see, 1404 plus 2.75c is equal to 1061. I can combine like terms on the left-hand side, right? Negative 5.20c plus 2.75c is just negative 2.45c. And then I will subtract 1404 from both sides. I'm going to get negative 2.45c is equal to negative 343. And then finally, to get c by itself, I'm going to divide by negative 2.45. And that gives me c is equal to, it turns out to be 140. And it better come out to be a whole number, right? Because this, remember, c represents the number of children. So it looks like we did things correctly. We have 140 children. Now, how do I go back and find the number of adults? I plug back into either of the original equations, but remember, when you're using substitution, you should go to the one that you already manipulated. You already isolated the a here. So go back to that equation and plug in your c to solve for a. So in this case, a is going to be negative 140, right? Because remember, c was 140, plus 270, and that's what, 130, right? So a equals 130. So that's the answer, right? We know that there's 130 adults that attended and 140 children. Okay, that's a very typical type of application for a system of two linear equations and two unknowns. Okay, here's another one. It says, if Ricky has 13 coins, all dimes or quarters, in his pocket for a total of $2.20, how many of each coin does he have? So again, create variable names. Let's say, so we want to figure out the number of quarters and number of dimes, right? So let's say Q represents the number of quarters, and then D represents the number of dimes. So the first equation is going to involve the total number of coins, right? We know that if I add the number of quarters, Q, plus number of dimes, D, that has to equal 13. So this just deals with the total number of coins. And the second equation is going to deal with the total value, right? The total amount of money. So how much is each quarter worth? Well, each quarter, we're dealing with dollars, right? It's 25 cents, but in terms of dollars, it'd be 0.25. So I can write this as 0.25 times Q. Basically, it's saying $0.25 per quarter times number of quarters is the total amount of money I have in quarters. Plus 0.10 times the number of dimes, that's the amount of money I have in terms of my dimes. That's going to equal the total amount of money I have in my pocket, which is $2.20. Or that Ricky has in his pocket, right? So this is second equation deals with the total money. Okay, again, we can solve it many different ways. You could get rid of the decimals if you want by multiplying the second equation by 100. Let's just use substitution again. So I'm going to solve for, say, Q in the first equation. So that I'll just subtract d from both sides. So I have q is equal to minus d plus 13. Then I'm going to go to the second equation, and where I have a q, I'm going to substitute in negative d plus 13. Okay, so I have 0.25 times negative d plus 13 plus 0.10 d is equal to 220. Distribute, so I have negative 0.25 d plus 3.25 plus 0.10 d is equal to 220. If I combine like terms, right, I have negative 0.25 d plus 0.10 d. That's going to be negative 0.15 d plus 3.25 is equal to 220. Then I'll subtract 3.25 from both sides. So I have negative 0.15 d is equal to negative 1.05, I guess. And then divide by negative 0.15. And if you do that, you're going to get d is equal to 7. Again, good thing it came out to be an integer, right? Because we can't have like a fraction of a coin. So it makes sense that d is 7, right? So the number of dimes is 7. And then to go back and find a number of quarters, I'm just going to plug into this equation, right? The one I already isolated, the q. So q is equal to negative d plus 13. So it's going to be negative 7 plus 13. Which is 6, right? So number of quarters is equal to 6. So basically, Ricky had 7 dimes and 6 quarters. Okay, and it makes sense. I mean, you can check it, right? If you have 6 quarters, what's the total value? It'd be $1.50, and then 70 dimes is 70 cents. $1.50 plus 70 cents is $2.20, right? So it checks. Okay. Oh, here's another common type problem. You're told John is 3 years older than Amanda. In 9 years, the sum of their ages will be 69. How old is John now? Okay, so again, create variable names. Let's say the age of John now, I'll call J. And the age of Amanda now, I'll call A. So one equation is I know now that John is 3 years older than Amanda. So the way to interpret that is J equals A plus 3. Right? If John is 3 years older than Amanda, then John is going to be Amanda's age plus 3. And then in 9 years, it's saying that the sum of their ages will be 69. Well, how old is John going to be in 9 years? Well, John will be J plus 9. Right? And then how old will Amanda be in 9 years? Amanda will be A plus 9. So if I add those together, I must get the sum. It's saying the sum of their ages is 69. Okay, so, and you can simplify this equation, right? I can simplify this to J plus A plus 18. I'll combine like terms, equals 69. And if I subtract 18 from both sides, I'm going to have J plus A is equal to, was that 51, I guess. Okay, so now I have my two equations out. I have J equals A plus 3, and then J plus A equals 51. Okay. It looks like this is set up to solve using substitution, right? Because the j is already isolated. But just for practice, let's use elimination, just for some practice. So remember, for elimination, I have to make sure that the variables are lined up on the left-hand side. So I'm going to subtract. I'm going to take that first equation. I'm going to subtract a from both sides. Oops, this is plus 3. So I can write that first equation as j minus a is equal to 3. And then the second equation I can leave, right? The j is there plus a is equal to 51. Now notice, actually, this is nice because I don't have to do anything else. I already have my coefficients are equal and opposite on the a's, right? I have -1 and a +1. So immediately I can go to adding these two equations together. The a's are gone. I'm going to get 2j is equal to 54. Divide by 2. And I know the answer for j, right? J is going to be, what's 54 divided by 2? 27, right? Yeah, 27. And then to go back and find Amanda's age, I can plug into any of the equations. Let me just plug into the first equation. So I have j is equal to a plus 3. So I have 27 is a plus 3. I'll subtract 3. It looks like Amanda is 24. Okay, so basically we know that John is 27. And Amanda is 24. Right? Years old now. Remember, the A and the J are their age right now. Oh, and I think it asked for just John's age, right? So the actual answer would be just 27, right? John is 27. Okay, and then let's do one more example of an application. This one's a little bit trickier, but still doable. So it says the sum of the digits of a 2-digit number is 7. When the digits are reversed, the number represented by the original digits is increased by 27. Find the number. Okay, what does that mean? Well, for my 2 digits, I'm going to use, say, just x and y, right? So I have a 2-digit number. The x, think of the x as like in the tens place, and the y is in the ones place. And the first equation is easy. It just says the sum of the 2 digits, so x plus y, has to equal 7. Okay? But what is the original, what's the number represented by the original, like what's the value represented by the original number? So here, you have to think about this a little bit, right? Because the x is in the tens place and the y is in the ones place, the actual value of this is going to be 10 times x plus y. Does that make sense? Like if the number were, say 22, then the actual value is 2 times 10, right, is 20, plus 2 times 1. You could say this is 1 times y. Right, so it's 10 times x because it's in the tens place and 1 times y. Okay, if reversed, then the number is going to be y, x, and the value is going to be 10y plus 1x. Right, of the reverse number. So the value of the reverse number is 10y plus 1x. Okay, and what this is saying is when the digits are reversed, right, so that's this case, then the number represented by the original, so when the digits are reversed, the number represented by the original digits is increased. So this is the number represented by the original digits, is increased by 27. So basically the second equation is going to be the new reversed value, which is 10y plus x, is equal to the original value, 10x plus y, plus 27. So that's our second equation. This is our first equation. This is our second equation. Now, we can simplify the second equation, right? Let me subtract 10x on both sides. I'll subtract y. Let me do it this way. I'll put the x's together and then subtract y. So that second equation is really going to be 9y minus 9x is equal to 27. And the first equation was just x plus y equals 7. Okay, and then of course I want to, let's say I want to use elimination. So I better write these. I'm just going to do this by erasing. I'm going to write these in the right order. So I want the negative 9x. So the x is lined up. So I want that first. And then plus 9y. I'll do that second. Okay. How do I eliminate these? Well, let's eliminate the x's. So I already have a negative 9 here. Let's make this a positive 9. I can do that by multiplying the first equation, both sides, by positive 9. So I'm going to have, if I distribute this, I'm going to have 9x plus 9y is equal to 63. And then, so I'll write it down here again. And in the second equation, I can just leave. All right, so now I add them. The x's are gone, right, by design. The y's, I'm going to get 18y is equal to 90. And then if I divide by 18, y is equal to, I guess that's 5, right? So y is 5. And then I can go back and solve for x by using the easiest one is the first equation, x plus y is equal to 7. So I have x plus 5 is equal to 7. Subtract 5, subtract 5. So it looks like x is 2. Okay, so what does this tell us? Well, this tells us, remember, the original number is what we're looking for, was written as x, y, right? The x is in the tens place, the y is in the ones place. So this is saying that the original number is 25. Does that make sense? Let's actually look at the answer and see if this makes sense with the original problem. So it says the sum of the digits is 7. Is that true? Yeah, 2 plus 5 is 7, so that works. When the digits are reversed, so if these are reversed, right, you'd get 52. The number represented by the original digits, 25, is increased by 27. So is 52 equal to the original number plus 27? Yeah, that's 52, right? So that checks. So we know that that's the correct answer. So the original number was 25. Okay, that one was a little tricky. The other types of problems are more general that you see often in many textbooks, like finding the number of adults and children at a fair, that sort of thing, or the number of coins in a pocket. But there's many types of examples like this that we could use. All right, next we're going to get into quadratic and polynomial functions. Okay, so this is sort of the end of linear functions, and we did this one unit on systems of two linear equations and two unknowns. Great, thanks.